In this lecture, we will start a new topic on color fundamentals and processing. So, let us try to understand what is meant by color and how do we perceive color. Color is a psychological property of our visual experiences when we look at objects and lights. It is not a physical property of those objects or lights. It is the result of an interaction between physical light in the environment and our visual system. Consider the electromagnetic spectrum, the broad range of electromagnetic spectrum starting from a very long wavelength of radio waves, long radio waves to say gamma waves, and you can find there is a very narrow interval in this particular spectrum at the higher end of spectrum frequency, and that is that consists of the visible spectrum. Those are the frequencies of lights or colors what we perceive, and it has been shown here pictorially that how these wavelengths correspond to different colors. You can find that in our school textbook when we learned about this phenomena of color in different optical bands. So, there are 7 particular colors of rainbow that was distinguished, and you can find out that from violet to red, that famous acronym of VIBGYOR, you can identify those spots in this particular picture. So, interestingly, our sensitivity to this part of spectrum is very high, and if we see the curve of this luminance sensitivity function, which is a function of the wavelength, and we can find that it is maximally sensitive when in the green zone. That is what it is shown here, and later as we move towards the either towards higher frequency range of violet or violet zone and or lower frequency range of infrared zone, there this luminance sensitivity function slowly gets decayed. The thing is that the light which is causing this sensation, that may not be also having uniform energy distributions over all the wavelengths. So, there is a relative spectral power, we call it relative spectral power. It is the energy per unit time, that is what we need to consider here. And for example, this could be a signature of a light source, where you have a relative spectral power distributions over these wavelengths. So, this is how a source of light is described. It is the amount of energy emitted per time unit, I mean that is the power at each wavelength from 400 to 700 nanometer, and that is the visible band of this electromagnetic wavelengths. So, some examples of these light sources, if we consider a ruby laser, it is a very pure electromagnetic wave radiator at the near about 700 nanometer, which is the red, in the red region, the color is red. Whereas, see these are other examples, gallium phosphide crystal, or if we consider normal daylight, more or less this spectrum is uniform, that you can see here. So, one of these particular characterizations of this luminance source is the black body radiators, which is an ideal energy emitter in that sense, and which does not have which only absorbs from the environment and have its own energy spectrum. So, one of the example of for constructing a black body could be a, let us say, first this is a hot body with near zero albedo, or that is why it is black body. If it does not reflect the light from the environment, then no, we cannot see it. That is the concept of blackness in this case. And the easiest way to do this is to build a hollow metal object with a tiny hole in it, and we can look at this hole. So, the inside it becomes it's an ideal black body radiator, and the spectral power distribution of a black body radiator, it is a simple function of temperature. So, which is radiating, and this is that famous relationships of energy emitted in power wavelength, energy power emitted power wavelength, that you can see here, and this is proportional to this factor, where you know that this h is that Planck's constant, and you can find, and k is the Boltzmann constant. Those are not defined here. So, it just shows that the kind of functional relationships between the temperature and the wavelength, and the distribution of energy with respect to wavelengths given a temperature. So, this leads to the notion of a color temperature, because if a light source, it has its own spectral power distributions, or if I say energy emission distributions over the wavelengths, and then which one is closely resembling to this of a black body radiations of a particular temperature, we consider that source is equivalent to having a black body source of that color temperature. So, we can tag any luminance source by any color temperature. From there itself, we can get its spectral power distribution. So, this is the temperature of a black body that would look the same when you are considering the notion of color temperature. Let us now consider that the phenomena of reflection in the environment, because this reflection is the major phenomena by which we sense the environment, we see the objects that we have discussed from the very beginning itself. In our very first slide, we considered reflected light's projection of three-dimensional scene points to a two-dimensional plane. So, in our visual system also, we are getting reflections from a three-dimensional scene, and it is basically falling into our retina of eyes, that I will be discussing in my next slides. But the nature of that reflected energy, that also depends upon the kind of surfaces you have. So, every surface it absorbs a part of its incident energy and also reflects, and in different wavelengths it performs this job in differently. So, if I consider the percentage of light reflected across wavelengths, that also shows the material property of that surface with respect to this particular task. For example, you can see the picture of tomato here, which is of red surface. So, it is expected the energy what is reflected from these surface points, they will have high content of red wavelengths or the wavelengths, higher wavelengths in the optical range. Those are the part of that energy of the reflected wave. For banana, which is yellow, the spectrum looks like this. This is a percentage of light reflected in different wavelengths, and it has high reflectance value of within this zone, and particularly the yellow zone is very prominent, including the red zone also, as you can see here. And this is the blueberries, and naturally it is expected that the reflection in the blue range of the visible spectrum, those will be high. And this is another object which is of purple color, and there we can see that the reflectance in this interval is very low, whereas in this particular zone, even in the blue zone and also in the red zone is quite high. That is interesting, that you have the purple reflections, but still you have sufficient component of red zones and blue zones. There are explanations of these behaviors of our visual response. So, finally, as we can see that it is the interactions of light and also the material property of the surface, light source and the material property of the surface, that results into our visual sensations. So, that is what we observe as a color. So, if I consider and a light source, so the reflected energy distributions across wavelengths in a light source, and also the consider the reflectance values or percentage of reflectance reflected energy from surface points and from surfaces at different wavelengths. So, for every wavelength the energy what we receive in our visual system, that is simply product of these two factors, that is the power of illuminations or reflect or the the relative energy of this particular wavelengths, the energy of this per any wavelength, and also consider the corresponding reflectance value of that wavelength, you multiply, and then you get the relative energy of that particular wavelength. That figure you will get in the received signal. That is how the received signal or received sensation is or received sensory signal, if I say exciting signal, that is how it is characterized in this way. So, now let us consider the function of our eye in our visual system. Now, it is acting like a camera, as you can see in its construction. Say there is a lens, and that projects the three-dimensional points in a environment to a two-dimensional plane, or to, and in fact it is not a plane, it is a spherical, I should say it is like a spherical screen where these points are projected, semi-spherical screen, and that is called retina, where these points are projected and sensation is carried out from that point through our nervous system to our brain to understand to which gives us the perception of this color, and also we can understand the scene what is there in front of us. So, the components in this part which has a very direct analogy with the function of different components of a camera. You can see lens is this part. Similarly, the retina where there is a screen kind of thing which acts like an image plane, and there are photoreceptor cells which carries the sensations, which transduces this energy into the electrical signal form. So, the retina consists of these photoreceptor cells, and from there the sensation is carried to our through our nervous system to brain. And there are different kinds of photoreceptor cells in our retina. They are called rods and cones. So, I will give more details in next slides. Here there is also an iris which is in colored annulus with radial muscles, and there is this pupil, the hole or aperture, and like an aperture of a camera through which the optical lights, the energy is transmitted through the lens, or lights are coming to the system, entering into the system, and this is like an aperture of a lens, and its size could be controlled by the iris. So, about the rods and cones, there are two types of receptors in the retina that I mentioned. The shape of cone and rod we can see here. They are cells, basically they are cells, and they are attached with the corresponding optical nerves which goes to our brain through optical through the nervous system. There is a pathway through which the sensation is carried out. Is carried towards them, and this is attached to this particular retinal surface. This is the attachment surface what is there, and the shape of this attachment as relate to the nomenclature of this kind of cells. So, this is, since this is a conical shape, we call it cone, and this is a cylindrical shape, we call it rod. Now, the distribution of these rods and cones, that is not uniform over this retina. So, you can see that cones are highly concentrated over this. So, this is the distribution of cone, and cones are highly concentrated over the retinal part. So, let me just point out. So, this is what is the is a distribution of cone roughly. This is a distribution of cone, that is the curve what is shown here, and the outside the curves, they are the distribution of rods, and it is very much concentrated on a particular region, and which is a very small high visual acuity region, and which is called fovea. So, this region of the retina is called fovea, and here the degree that is formed in this region is a very narrow degree of, it forms a very narrow degree, about 1 to 2 degree of range. So, if I the function of rods, that it is responsible for intensity, and cones it is responsible for color, and the fovea, as I mentioned, it is a small region that is 1 or 2 degree at the center of visual field containing the highest density of cones and rods. So, this is how the structure is there, and in the periphery we have less visual acuity. There are many rods wired to the same neuron. So, that is the kind of structure. So, let us try to understand how rod and cone, they are responsible, they function, they are responsible for sensing the the light, and their sensitivity, we can see it varies. Rod vision, it is sensitive to low illuminated environment, whereas cone vision is more sensitive in a very highly in a bright or highly illuminated environment. So, you can see from these particular variations, it is shown here that this is a zone which is for the rod vision zone, and this is the zone which is for cone vision zone, and this is the scale which is showing the intensity of lights reflected from objects, and follows the Lambert, the unit is a Lambert unit. So, if I say what is a Lambert, 1 Lambert, it is basically the definition is in this way, it is 1 by pi candela per square centimeter. Candela is an again unit of energy radiation. So, it is the luminous intensity in a given direction of a source that emits monochromatic radiation of a frequency of this 540 terahertz frequency, and that has a radiant intensity in the direction of a particular power per steraradian that is being emitted, that is 1 by 683 watt per steraradian. So, if this is a kind of a intensity, this is a kind of intensity or energy emitted from, this is the amount of energy emitted per steraradian at that frequency and from a source, then that unit is 1 candela in that given directions, that is. And if it is 1 by candela per square centimeter, then the intensity of that surface at that point 1 Lambert. So, that is the definition, and for very high intensity object points, we will be able to perceive through cone, whereas low intensity visions are through rod. So, visual acuity is more active in the cone sensitive zone, and that is why we cannot read, we are unable to read in low illumination, because rod vision is not visual acuity of rod vision is less. So, now let us understand then with this background the physiology of color vision. So, as we have seen, there are 3 kinds of cones in our visual system, and you can see that there are 3 responses, like this is one kind of wavelength, this one kind of response which is shown here as the S, and or short wavelength response, and that is the response in the blue zone. There are medium wavelength response which has been shown here as M, and there are long wavelength response. So, there are 3 types of cones. So, it is cones are also, there are 3 categories, and they have different types of wavelength responses. And so, the ratio of this long wavelength, medium wavelength and short wavelength cones, they also widely vary. As you can see that more number of long wavelength cones are in the red zone, that is ratio is 10, whereas in the medium wavelength it is 5 and short wavelength it is 1, and almost no S cones in the center of the fovea. So, in fact, there is a nice picture which shows the distribution of different types of cones by showing the colored dots in this particular two-dimensional point. So, if we flatten the retinal surface near the fovea particularly, and you can see in the central part hardly there are blue cones or short wavelength cones, mostly it is red and the green cones or medium wavelength cones that we can see in this picture. So, just to model this color perception, we can consider this particular simple mathematical explanation or mathematical model, that let us consider the incident energy in our retina having a relative spectral power distributions as shown here across the wavelengths. And then you have the same sensation is received by 3 different categories of cones. So, we will be explaining the color perceptions only using the cone vision. So, we are not considering rod vision in perceiving colors. So, the color perception is a phenomena due to our sensations through cone cells, and there the same sensation is same energy is received by different kinds of cones, but they have different different effects or responses, because they are wavelength response, they are wavelength or their response to their wavelengths are different. For example, this is the long wavelength cells, this is the filter response for long wavelength cells, and this is the filter response for medium wavelength cells, and this is the filter response for short wavelength cells. So, as we have considered the simple model, that what we can do, if I consider this received energy can be shown as say E lambda, then in our long wavelength filters in the long wavelength cones, the received energy can be modeled as E lambda L lambda. So, what is being finally received the output of this output from the long wavelength cone is E lambda L lambda. So, it is the integrations over lambda, and that should be the response from long wavelength cone. So, if I write this response as CL, so this is what we will be obtaining from a long wavelength cone. Mathematically, this is the operation that is being carried out there. Similarly, for the medium wavelength cone, we can write it as E lambda So, this is the response, this is the output of the filter with the spectrum with its frequency spectrum as say m lambda, or wavelength spectrum as m lambda, that is the filter response, and then this is the output we get from that medium wavelength cone. And for short wavelength cone, in the same way we can write it as E lambda S lambda. So, now you can see that given a particular energy, particular energy from the environment which is received by all these cones, we can finally this can be coded into 3 factors, one from the long wavelength cones, another from the medium wavelength cones, another from the short wavelength cones, and those sensations are carried to our brain through the nervous systems, and those are perceived as a color. So, finally, color perceptions can be considered into this form, that it is the effect of these sensations which is giving the ultimate which is resulting into the perception of the color of that particular light. And this actually leads to the trichromacy theory of color, which I will be describing next. So, just to summarize once again, in this color perception, we have entire spectrum and entire spectrum of reflected energy from an object or energy of an illuminant that could be represented by 3 numbers, as I explained how these numbers could be mathematically computed given all these facts. And then it also tells us that even if we have different spectra, it can have the same representation, because finally as you can see there are it could lead to the same set of triplets by doing that product and integrations over accumulated accumulations of this product of the corresponding response and also the power over the wavelengths, that would give you the same vectors. So, it becomes indistinguishable, and such spectra they are called metamers. So, there are some examples of this metamers we can see here. Consider this spectra or the relative power spectra for different kinds of reflected waves. Say this is a white petals spectra, which has been shown here by this particular color, and another in this pink curve, this is a white flower, and our sensation of white petal and white flower is similar. It is a white sensation, and but as you can see there is a lot of variations over the distribution of the relative power over the wavelengths in these 2 different sources, but still we perceive them as white, and this is an example of metamer. There could be another example that you can see that this is a widely varying relative spectra, relative power over the wavelengths, whereas there is a smooth variations, but final effect of integrations of the product of our cone response and with this energy distributions, with these power distributions of a particular at a particular wavelength, final effect may be same, and that is how that it could be also another pairs of metamers. So, with this let me stop at this point for this lecture. We will continue this discussion of color perception. Thank you very much for your attention.